we're going to talk about Joseph Priestley. He lived from 1733 to 1804, and he is credited with discovering oxygen. You'll see that Priestley there's two E's in Priestley, L-E-Y. Sometimes you see it with one E, Priestly, but mostly it's spelled with L-E-Y. Now, I wanted to put this in context, in the scientific context of understanding the nature of matter, which has been a scientific process which has been going on for a very long time, as Archie Bunker would say, since time immemorial. It's really been a very long time that people have wondered what in the world matter is. And it began with, now probably Tony can correct my pronunciation of these characters, but at least the written record of trying to investigate matter goes at least back 2,500 years with Empedocles. And he was Greek. He lived in Acraga, Sicily. This is over here. That was part of the Greek Empire at the time. His Greece over here and his Sicily there. Now at that time, he and they, 492 to 432 BC, he lived. They believed earth, wind, fire, and water were the fundamental elements of components of all matter. And different ratios of those four categories resulted in different forms of matter. Now, science then isn't what science is now, but it is a form of analysis. And they had a key concept, which was that matter consisted of discrete and quantifiable components. That they had right, and that's sort of the beginning of the process. But of course, the flaw is that there are an infinite number of combinations. There are an infinite number of forms of matter, which simply isn't true. So then, I don't know how to pronounce his name, but it's Demokritos, I guess it is. And he lived in Abdera, Greece, a little later, 460 to 370 BC. This is Greece, Macedonia, and here's Abdera. Can you see my pointer? I can't hear any voices.
Yes.
Yeah, okay. So this is a nice picture of Abdera. This looks like a nice place to visit for a week, just sort of hang out. And what he noted was that a stone could be broken into progressively smaller pieces. And he hypothesized that at some point, the particle would become indivisible, that means atomos. And now this is the key concept of understanding matter, that there are fundamental particles to matter. And this is around 400 BC. So this was a major step in understanding matter. And that basically what he said, he figured out that everything is made of atoms, indivisible, at that time, indivisible particles. All he had to do was fill in the periodic table and go to lunch, all done. And yet it wasn't until 1869 that Mendeleev started working on the relationship of the various elements, and this is an early copy of his periodic table that he was working on, because there was a big problem, and the problem was a fellow from the north area called Aristotle from Stagira, I think it's pronounced Stagira, Greece, up in here, and so he's 385 to 323, and he believed in earth, wind, fire, and water. And he didn't take much truck with the idea of things there being atoms as fundamental particles. So here we go. The initial timeline was Empedocles, earth, wind, fire, and water. This is 500 BC here. Then Demokritos, atomos, and then right back to earth, wind, fire, and water. So it looks like Aristotle just didn't like a paradigm shift. And paradigm shifts can be painful. And his error was, I think, one of the two greatest errors in science ever made. The other error took place at the library in Alexandria, Egypt. This was the great library. They had something like 400,000 scrolls containing about 2,000 years of math and science knowledge. It was founded in 250 BC. The error was made by the plant manager in 270 BC when he said that all of the fire safety equipment was in good working order. Didn't work out that way, and it burned down with the loss of all those scrolls. Now, the title is If Ifs and Buts Were Candied Nuts, We'd All Have a Merry Christmas. Had Aristotle accepted the paradigm shift, this is my opinion, the search for elements would have started rather than remain in limbo for 2,000 years. And this comes down to how science works, science and human nature. Humans are innately curious creatures. We just are. And we wonder about things and we make tools. And science advances in a structured way. It's not a random event. And this is the virtuous cycle of discovery, where you have something or other that's discovered, you have experiments and measurements, then you get data, and then you have a hypothesis and a working model. Then somebody gets some new equipment, and you experiment and measure, and you get more data, and a new hypothesis, a new working model. It goes around and around and around until finally you get a real a real model, and then an application. And we saw this when Dan Kleppner gave that great talk on the atomic clock. He described the going around this virtuous cycle for, I don't know, 30, 40, 50 years, something like that, and where he showed the slow development of the atomic clock. And this is the natural way science works. Of course, truth be told, it doesn't really work that way. There's many a blind alley that people go down. But these people are all forgotten, of course, and then it goes around and eventually we get to a model, but we'll let that go. So scientific progress is interrupted by war, religion, natural disasters, and the worst of which was the named by Petrarch, 1450, the age, seculum means age, seculum obscurum, the dark ages, where almost no science was done at all. And that lasted 1,000 years. A little bit of setback. Now, here's where I come to my speculation about what would have happened. The Greeks had smelting of iron, and the Iron Age began around 550 BC. And by 300 BC, iron was everywhere, went all around the Mediterranean, up into southern England, into Europe, for what it's worth there. It's primitive there. It was everywhere. Now, Tutankhamun had an iron dagger in 1200 BC, but that dagger was 11% nickel, and iron ore is not hardly has any nickel in it. It's thought that that was actually from a meteorite, which does have a high nickel content. But they had kilns in the Iron Age. They could get to 3,800 degrees Fahrenheit, it's 1,500 centigrade, and they could have converted any number of oxides to base elements and started working them on them. And people just would have invented things to look at those products and figure out what in the world they were and work out relationships. But instead, well, here, let me look. Here's the periodic table of things I think they would have found, because they're in abundance. Aluminum, silicon, they would have found. Let's see, zinc they had, nickel they would have found, manganese probably. They probably would have killed a whole bunch of people figuring out what sodium was. There's tons of magnesium and calcium in seawater. They would have found that. They would have had silver here, gold. They had gold, so they silver. They had lead. They would have gotten a lot of it and gotten started on doing things. But it never happened. And we literally fast forward 2,000 years to Evangelista Torricelli. And this was one of the most important measurements in science. At that time, there had been a lot of progress in metallurgy, glass blowing, weights and measures. They used pounds. Every region had their own ounce and pound, but they were convertible with a little arithmetic. And what Torricelli did was, let me just go his age here. He lived from 1608 to 1647. I put Isaac Newton here, down there, 1643 to 1727, because Isaac Newton his life was the great divide in science. He was science before Newton and science after Newton were just very different, and his period was just a major shift. It was sort of like World War I or the discovery of nuclear fission, where the world afterwards is different than the world before it. So Torricelli, he died in 1647. So he was putting out on the 18th hole when Isaac Newton was just starting out. So he was before Newton. And what he did was he took a glass tube with a closed end here. This is closed, and he put it in mercury. They had lots of mercury. Hatters used it for felt. There was lots of mercury around, called quicksilver. And he filled this tube completely with mercury, all the way up sideways, and then flipped it up so that there'd be a vacuum here. And at the time, it had been a mystery why pumps could create vacuums, but they could only pull water up so high in a column and it wouldn't go any higher. And what Torricelli figured out was that there's nothing in a vacuum, and a vacuum doesn't pull, but rather it's the weight of the atmosphere that was pushing on the mercury to make it go up the column. And he took his barometer. He didn't have that as a measure, but didn't have that word, but he took his barometer and he took it up on high hills, and lo and behold, the pressure went down. And he took it into valleys, and the column went up, and he figured out the weight of the atmosphere on there. And he figured out that the atmosphere was an earthbound phenomenon by the rate of which that pressure was declining, that it didn't go up forever into the heavens. He didn't know how far it went, but he knew it was declining in mass a lot, just in a few hundred feet. And now, only pulmonologists deal with this. The unit of measure, 1 millimeter of mercury, is 1 torr, and that's for Torricelli. Now, so basically what Torricelli was in the equipment phase of the virtuous cycle here. So he created an efficient, cost-effective vacuum in a tube. And Torricelli created the basis of measurement of equipment for the discovery of gases. And here he's got a mercury bath, and he's got a mercury tube there. And Torricelli was no one-trick pony, and he's had influence on our group. He showed that projectiles sent out parabolas at the same speed in all directions tangent to a common parabola. This is what ballistics are. And we had our lecture on finding the direction of bullets by the shock wave that the bullet produces. It's based on this parabola. And also, he gave the first scientific description of the cause of wind. Winds are produced by differences of air temperature and hence density. Now that's a big concept. Between two regions of the earth. And we have a subgroup studying climatology. He was kind of the first climatologist, I guess. And now this brings us to what Priestley believed in, which was the Phlogiston Theory. And this can be very confusing. Now you'll have to interrupt me because with the way I have this set up, I can't see the chat. I can't make it come up. But this can be confusing. Now, phlox, Tony, this is an ancient Greek word. I hope it's right. Greek word for flame. And it was proposed by Johann, his name is Becher, according to my sister, who speaks German, 1635 to 1682. He proposed this theory, which we'll go over, and it was promoted by George Stahl in the early 1700s. So we have Torricelli before Isaac Newton, and Becher was just around the time of Isaac Newton. Now here's the phlogiston theory that Priestley was working with. If phlogiston is a fire-like substance, phlogiston, contained within combustible matter. That is, the flame actually exists within the matter and is released during combustion or heating. So you have wood, and when wood burns, it gives you phlogiston and ash. When wood burning took place, the phlogiston was absorbed by the atmosphere until the atmosphere was saturated, at which point the burning stopped. The problem was that some items like wood became lighter when burned, and others like aluminum become heavier. So you take some aluminum, you burn it, you oxidize it, you burn it, and you get a heavier product. So this is a weakness of the theory, that sometimes phlogiston had weight and sometimes phlogiston had levity, which was a problem with the model as we're going through our virtuous cycle. So was Becher all wet? No, it really wasn't. First, he figured out that matter contained mass and energy. This is an enormously important concept that matter contains mass and energy. Now his model, yeah, it needed a little tweaking, but the virtuous cycle of scientific discovery would just take care of tweaking the model. He had it, even though it sounds crazy. He had it that matter was made of energy and mass. His error, of course, was that the energy was absorbed by the atmosphere. It was a flame that was absorbed by the atmosphere as the flame itself, and the mass, of course, became ash and soot. So along comes the Reverend Stephen Hales. Now, Stephen Hales was the great whatever grandfather of Charlie Hales. Charlie Hales was a pulmonologist at Mass General Hospital. He ultimately became the head of the he was a general pulmonologist when I was there. He became Charlie became head of the department. So this is like a family business, being in respiratory. So this is the Reverend Stephen Hales, and he invented a very important device called the Pneumatic Trough. And I'm going to go through this one because this is the simplest one that he made. And then when you had good craftsmen, they made much better ones. But here's the idea of a pneumatic trough. And this is the measurement equipment phase of the virtuous cycle. He took a bucket of mercury and an inverted glass bottle. You can think of this as a squat Torricelli tube. And he filled it with mercury, flipped it over and created a vacuum here. And here, this is just suspended here for stability. Then he would collect the gas. Now this diagram shows it coming from a fireplace to collect the gas up in here, and it would be sealed in a vacuum. In fact, he didn't really do it away. What he had was a bellows here, and you can see the fellow blowing in here. The bellows could be placed, say, in the fire and expanded and pull the gas out of the fire, then attached to the hose here and pumped into here, into the vacuum here, and be a well isolated atmosphere, what they would call it. They had the word gas, but they call it atmosphere. They could isolate the atmosphere. And this was an important piece of measurement equipment that allowed people to isolate various gases. To us, from our chemistry classes, we would diagram it more like this. You have a bottle or a flask, and you heat it up here, and you get a gas coming off here, would come down here and be collected in our inverted bottle here. But it's really the same principle. And they got better made and progressively more complex. And we'll go through this diagram twice. First, this is the pneumatic trough. This is a wood trough filled with mercury, quicksilver. This is an inverted Bernoulli tube here and another inverted Bernoulli tube. This one is a gas being collected from something else. It would be, I'll show you later, it would be collected, and then it would bubble up into this tube. I have no idea what's going on in this tube. Over here, this is an inverted Bernoulli tube now placed in this one here with a plant growing in it. This is just another Bernoulli tube, and these are mice that people will experiment in by somehow moving this gas into the mice container. So now we get to our man of the hour, which is Joseph Priestley. So he would live from 1733 to 1804, born outside of Leeds, England. And his family were dissenters, so they didn't conform to the Church of England. So he couldn't enter British universities, and he couldn't become a trained scientist. But he was a man of means. He was raised by a wealthy aunt and uncle. Now, he believed in the Phlogiston Theory, but he wrote some things about science. He wrote, scientific progress depends more on the accumulation of new facts that anyone could discover than on the theoretical insights of a few men of genius. This was a shot at the British aristocracy, which kept him out of science and had their own sort of authorities who would just come out with dictums as to what was what without a lot of scientific evidence. And being a dissenter to the church, he wrote, prejudice and dogma of any sort present obstacles to individual inquiry and private judgment. So he was not all that good at making friends and influencing people. He had a lot of acid remarks which got into the press and didn't do him any good. Now, Priestley worked with a lot of things, and he worked with Benjamin Franklin to create his electrical machines. Here, see, there's no E in the Priestley here. Here's the power source. Here's where the electrons are stripped, I think. And here's where the positive charges would go, and the positive atoms would go. And here's where the electrons would go. And this is analogous to the Van de Graaff electron generator. The difference being they got a few volts here, and he got like 20 million volts in his machine. So it's a little more powerful, but it was the same concept. And Benjamin Franklin worked with him on this machine. Now, Priestley did a lot of experiments, and he tested many boiled and burned products. And this is supposed to be a vessel, and this is a heating element, a fire, and he would get them to boil up into here. He believed that he was separating phlogiston heat from matter. That's what he thought he was doing. He believed in the phlogiston theory. But he also wanted the data to fit, he wanted the model to fit the facts. So his most famous experiment is with mercuric oxide. It's also mercury oxide, same thing. Now, mercuric oxide, that's the deep orange stuff, forms spontaneously the bath of a pneumatic trough. That is, the mercury oxidizes and the red stuff floats up on the top. Mercury, as you know, because quicksilver is silvery. What he wanted to do was heat the mercury oxide to get the phlogiston out and see if the mercury was left. That is, he could isolate phlogiston in the collection bottle and have it isolated from the bath. He didn't have to have any other product, so it would be a pure experiment. So what he did was he took calx is a stone. So this mercury oxide is stony. He would take mercury oxide. He thought he would separate phlogiston and get mercury. Now that's important. That's what he's trying to do. Take the calx, he didn't know it was an oxide. Take the stone and separate the phlogiston from the mercury and get it in pure form in the bottle. We know, of course, that he was taking mercuric oxide and making oxygen, and it's not balanced, but he's making oxygen and mercury. The problem was that the melting point of mercury oxide is 32 degrees Fahrenheit, which is 500 degrees centigrade. And the boiling point of mercury is 674 degrees Fahrenheit, which is 356 degrees centigrade. If he heated that the Hales' pneumatic trough up, the whole thing would boil over and be a total mess. He couldn't do it. That was not possible to do that experiment with that simple bath. It just got too hot and boiled over. This is almost 250 degrees hotter than the melting point of mercury. But what he wanted to do, to go over it again, because it's confusing, he wanted to take the calx, mercury oxide, and his model, he would get phlogiston into the collection bottle and cooled mercury back into the pneumatic trough bath. That's what he wanted to do. So, and this is his sort of a model of his experiments. His bottles were very big. They weren't tiny little things like they're often shown. And this is a little device here to move gas from one bottle to another. Here, over here, this is a candle heating something up, and this is where it goes into that little container here, and then into the mercury and into the barometer here. This is another collection system where you just stick a pipe into the fireplace and collect it into the mercury, into the barometer here. And there's some other equipment. This is a collection bottle for experiments for mice or plants where you actually put the gas into here and then close this valve and seal it off. This is I'm not sure what in the world this is supposed to be, except it's a double Bernoulli barometer tube where you have both ends in mercury and a vacuum here. I don't know what they use that for. So now we have the upgraded pneumatic trough. This is the same one, a similar graphic as before. Wood, this is all quicksilver. These are just a couple of inverted Bernoulli tubes. Here's that little canister here, could be attached to something else, bubbling up into here to create the atmosphere. I have no idea what's supposed to be going on in here. This is a plant in a Bernoulli tube to see if it could grow in a gas, which is called an atmosphere, to see if this could grow there. And here are the mice that they experimented on. And people were aware that Priestley experimented with mice. And he got some bad press about that. It was in the local press. There were no investigational review boards. And people were concerned about what he was doing with the mice. And there was a poem which I couldn't find, which I'd seen in the past about Priestley's use of mice. So people were aware of it and concerned about it, but he did it. So there we go. So what he did was he sent to London and got a 12-inch magnifying glass so he could focus the rays right on the mercury calx without heating up the, because it floated, without heating up the bath. And he took it out in the bright sun, so I'm sure it was up here, not over here, and he focused it right on that mercury calx, and he got it real hot so that it could separate the phlogiston from the mercury. Okay. Now, when he did that, he thought he collected a bottle of phlogiston. He had it in pure form. That's what he thought he had. But of course, he actually collected a bell jar full of oxygen. I mean, we know that, but he didn't know that. He thought he had phlogiston. Now, what was well known was here, this shown here. If you burn a candle in the closed jar, the candle will burn and it will go out. And he thought, well, if the atmosphere was saturated with phlogiston, and it was known that if you put a mouse and a candle together, the phlogiston would get into the atmosphere and kill the mouse. So therefore, since he thought he had collected a bell jar full of phlogiston, it should have killed the mouse and should not have let the flame burn. Does everybody understand that? That's his basis. Is anybody there? Is that clear?
Yes.
It's clear.
Yep,
Okay,
clear.
so now what happens? To prove his point, he puts the candle into the jar and the candle burned longer and quite brightly. So he was struck. He couldn't have phlogiston. He thought he had it, but he didn't. And he interpreted the jar could not be filled with phlogiston. So his whole theory of what he was doing was completely wrong, and he knew it. He knew that if he
say again what phlogiston is?
phlogiston is the flame. This is what makes it the model confusing. Phlogiston, that matter, this is Becher's theory. Matter is composed of flame, true flame. It's not something that happens. It's in the wood, or it's in anything. Then when you heat it up, the phlogiston will come out. But the flame exists in there. And then it comes out during combustion and it goes into the atmosphere and saturates the atmosphere. And when the atmosphere can no longer hold phlogiston, it's saturated, the flame has to go, a flame can no longer come out. That was the theory. So if he had phlogiston in this bell jar, it shouldn't have burned because it should have been saturated with phlogiston. But it burned for a long time, it burned brightly.
Can you explain again why he believed the mercury oxide contained phlogiston? What was the
because everything contained phlogiston. That was Becher's theory. All matter was composed of the matter and the phlogiston. There was that's all matter contained that.
Thank you.
That was Becher's theory. But now he was subject, it was being subject to experimentation, and it wasn't turning out too well. So he realized that the mercury that he had heated up, the calx, didn't contain phlogiston. It contained something else. So he started to experiment with what else it contained with. So here we go. If he had heated the phlogiston out of the mercury calx, then the atmosphere in the collection bottle should be saturated. The candle should not have burned, and yet it burned longer and brighter. So he was just perplexed by that. So here we go with the virtuous cycle of discovery. He thought maybe he's going down this pathway. He has to get more data. He has to work out the hypothesis in a new model. He has to go around this a few times to figure out what in the world is going on. But he was a clever man. So he called it dephlogisticated atmosphere. So when placed in a bell jar with dephlogisticated atmosphere, that is oxygen, a mouse would live for 1 or 2 days. Now this is not small like this. They were big vats. They weren't small like this little glass thing. And we know that if you put a candle and a rat together, the candle would, if phlogiston theory worked, the rat shouldn't live, but the rat did live. And I did a rough calculation, which is totally invalid. I used the oxygen consumption of a human being, which I'm sure is per gram, which is very different than the oxygen consumption of a rat, I'm sure. But I just, the only numbers I have are human ones. So a 2-liter bell jar with 100% oxygen would have enough oxygen for the very most 2 days for a mouse, but it's not just a few minutes as would happen with a candle when there's no oxygen in there. And likely Priestley's jars did contain 100% oxygen, but he had it pretty well done. See, this is what should happen, of course, is that the candle burns, the mouse dies quickly. Now he placed a mint plant. This was done sequentially, of course, but he placed a mint plant in the candle jar after the candle was there, and the mouse was placed in later, and then the mouse could live. Now what he was doing was, this was completely, this is hard to follow, but what he really did was, of course, the plant was creating oxygen, taking carbon dioxide out of the atmosphere. The reason this was inconsistent with the phlogiston theory was the plant was supposed to be made of phlogiston, so it should have rather than it should be made of phlogiston. So it shouldn't have reconstituted the atmosphere. I can't explain it exactly. I better move on. It's too confusing. So it's easier here. Oxygen here, CO2. He did this, and then he put a plant in there sequentially, and then the candle could burn. So he knew he was fooling with this, and that the phlogiston, if you think it through carefully, this doesn't make any sense for the mouse to be able to live. It's very hard to understand this on the fly because we're so ingrained in the oxygen CO2. We understand this completely. He didn't understand it at all. And this is this shows here the candle, the mouse dying. He puts the plant in there, and it reconstitutes, or it takes up the phlogiston, and the mouse can live and the candle can burn. But his initial jar wasn't supposed to have phlogiston. It was supposed to have phlogiston. The candle should have never burned. This is very confusing. So the air, because the jar air was reconstituted by the mint plant, and a flame would burn longer and a mouse would survive longer, which is inconsistent with the phlogiston theory if phlogiston was initially in the vat. So he was completely confused, but he did know the big story, that he had found an atmosphere that sustained life, and he knew that was very, very important as one of the great scientific discoveries. And he wrote, "I have procured air between 5 and 6 times as good as the best common air that I have ever met with." And that was pretty good because oxygen is 20%, the atmosphere is 20% oxygen. And so this is a pretty good estimate. And he knew that atmosphere was reconstituted by plants. He knew that if you burned a flame, the mouse would die. If you reconstituted, the flame would be gone. If you reconstituted with a plant, the flame could burn and the mouse would live. So he was confused. So he went off to Paris to meet with the father of modern chemistry in 1774. Before he went, he wrote up his results and he submitted them to the printer and got a receipt. Now, the father of modern chemistry was Antoine Lavoisier, 1743, 1794. He was born to the French nobility. He was well educated. He was born to wealth, and he ran La Ferme Générale, which during the period of the monarchy, the French government did not have an internal revenue service, but rather they hired a private company to collect the taxes. And Lavoisier ran that company. So not only did he start out with some money, but he made even more money by collecting taxes. Now, he did a lot of things with science. And one of the things he did was he took hydrogen and he burned it. He didn't know what he was burning it with. He just knew he was burning it. So he took hydrogen and oxygen from the atmosphere. He didn't know that. And he got water. So since this gas, whatever he had, since hydrogen generated water, he named the element hydrogen from water generating. So that destroyed any remnants of the theory of earth, wind, fire, and water were destroyed because he showed that water was not a fundamental component of matter, but rather could be generated from hydrogen, hence hydrogen. So anyway, so Priestley goes to Paris and he performs his experiments for Lavoisier. I suspect that all he took was his magnifying glass because everybody had quicksilver and everybody had these pneumatic troughs. So Lavoisier used Priestley's gas and he showed it combined reversibly with metals to form a calx. So he did the opposite experiment. And he found Priestley's gas in many acids, sulfuric acid, nitric acid. And since this gas seemed to be the genesis of acids, he took this ancient Greek word oxys, and since which means a sharp acid taste, and it generated the sharp acid taste, so he called it oxygen. So he didn't take much truck with the phlogiston theory. He was more into the theory of there being elements. And he showed that many substances when burned gained weight. And the idea that phlogiston had weight and at times had levity just became untenable. It just didn't work as a model. Now he also introduced Priestley even to stochiometry, the method of looking at the elemental components of substances. That's how Priestley should look at this. And this was an important step in the scientific method. And so what people had was descriptive terms, vitriol of Venus. He showed that it was made of copper and sulfate. So it was copper sulfate. There's a whole different way of thinking about things that were in front of you. And he worked out the nomenclature for stochiometry. He took, say, high oxygen acids like sulfur. The high oxygen he called sulfuric acid. In the low oxygen form he called sulfurous acid. And phosphorus, phosphoric acid with 4 oxygen, phosphorus acid with 3, with nitrogen, nitric acid with 2 is nitrous. And the salts, the high oxygen was an 8, sulfate, phosphate, nitrate, and the low oxygen was sulfite, phosphite, and nitrite. So people started talking about compounds and molecules as to their elements rather than these names that they had for them. Now there was another side of Antoine Lavoisier. He lived from 1743 and died in 1794 at the age of 50. Now, here's an important thing to remember. Being born into the French aristocracy just before the Reign of Terror it's not a good life plan. And running La Ferme Générale for the ancient regime, for the monarchy, is not a good career choice. Everybody hates tax collectors. And giving tax breaks to special interests has consequences. One of the things in France was that tobacco was taxed. It was taxed by the pound. Now the tobacconist claims that they added 1 ounce of ash to every 16 ounces of tobacco to improve the flavor. I have no idea if that's true. But Lavoisier taxed 17 ounces of tobacco at the rate of 16 ounces. And he was accused of conspiring to evade taxes and presumably taking a payoff by the tobacconists. And he was tried and he was found guilty and he was sentenced to be beheaded. But he was a towering figure in French science. And so it's kind of a good news, bad news. The good news was he had his sentence commuted a year and a half after his trial. That was the good news. The bad news was that he was beheaded 3 months after his trial. So the math didn't work out very well for him. So now we get to say, well, who really discovered oxygen? Because discovering oxygen, the gas that sustained life, is eternal fame. So Carl Wilhelm Scheele, he was Swedish, I think. He did lots of experiments with the same trough, with saltpeter, manganese, heavy metals, silver, mercury oxide, and he yielded the same gas, oxygen, in 1771. His paper went to the printer in 1775 and was published in 1777. A letter about these experiments was sent to Lavoisier in 1775 and, quote, never arrived, which is very suspicious. But Priestley cleverly had submitted his findings in 1774, shortly after his discovery and before going to Paris, and he got a receipt from the printer. Now, Lavoisier published a paper with Priestley's findings just after Priestley's visit, which aroused a little bit of a pique in Priestley. So was he a thief? Now, in a previous lecture, which I gave on COVID, I talked about Gonifs. Gonifs is Yiddish for a thief. And now one of the principles of Gonifs is they always leave a trail. And I talked about Sapan Desai. He's the man who ran the company Surgisphere, doctor ran the company Surgisphere. And they supposedly helped hospitals gather their data and their clinical data and convert it to its financial implications to help hospitals manage their finances. He falsified the hydroxychloroquine data in the Lancet article that had to be retracted. But in the talk, I showed how he had been falsifying data before. He had falsified data in his PhD program publication. He had altered the slides by cutting and pasting images to make the data appear like it wasn't. So he left his trail. So Lavoisier left his trail as well, because he may or may not have committed tax fraud, but he did commit scientific fraud. So he left a trail. You can come to your own conclusion, but he left a trail of fraud. So he was not entirely on the up and up. And that's the story of Joseph Priestley. Here in this figure here, it shows him burning things. These are newspapers, which were had a lot of negative articles about Priestley. And he was Priestley politician, or the political priest. He had a lot of things to say about politics because he was excluded as a dissenter. And here he is stomping on the Bible here. But that's the story of Joseph Priestley, and I'm sticking to it. It's confusing and hard to understand, but he had a model that was deeply ingrained in him, and he found it didn't work, and he went on to tweak his model, and here we are. I'm a pulmonologist. This is the basis of my career.
Yeah, but I'm asking a question about, I think he dies in Pennsylvania.
Yes, he did. He had a skedaddle. He was not in good favor with the people because of all his the bad things that he said, and he got himself in hot water innumerable times because of his comments about the world.